or equivalently family of a k-stable variety, and they sort of degenerate. What we can say about that? So a bit more precise situation, we are in a situation like that. We consider some kind of a family of the puncture disk of k-stable manifold. This is the algebraic side. But then on each fiber of this degeneration, we can plug in some unique canonical metric, the Kähler-Einstein metric, that you should think that in general, when t goes to 0, this metric actually degenerate from singularity, collapse, get a bit wild. And the problem, like the broad question is, how can we relate these two words? So this is the differential transcendental, this is the algebraic one. And the natural way to try to relate this problem is looking at limits. So we wanted to take the limits from the differential geometric side, and a very kind of weak starting point in looking at limits would be like look them as the underneath metric space structure and see which kind of metric space we have when we take limits. So this is like in the global outer sense, when we take sequence of points and we take what are the limits. Also important for today at a different scale, we can actually rescale the metric and see what happens when we take limits. So this is very natural from the differential geometric side. Algebraically, instead, when one wanted to study this problem of degeneration, one get a different way, potential study different way to filling in this family. With singular variety with different components. Of course, it's not unique, this feeling. And the problem is how these two things relate. And why do we care about these sort of things? So there are two interrelated reasons. One, if you take a more algebra geometric point of view, one can argue that the Kähler-Einstein metric are kind of the canonical metric structure when plugged in on this variety. So and they should have like some canonical limit, and the one can hope that by this limit induced by this canonical metric structure are telling us something about the degeneration of the complex structure, giving more canonical new perspective on the generation of the complex structure and formation of singularity. This is the algebra geometric like focus. If you have a more differential geometric focus, so Kähler-Einstein metric are important class of general Einstein metrics. From an analytic point of view, this is a very difficult partial differential equation to study. And the fact that you can create this link with algebraic geometry makes that at least in certain situations, like in this degenerate regime, you can hope to get some aspect of a computability of property of this geometric PDE, naming which kind of singularity they forms by relating to algebraic geometry that is much more computable than abstract relationships. So as I said, they don't focus only on the existence, but the idea is to focus what an analyst would say like a priori regularity aspect of solution of this Kähler-Einstein metric. So we want to understand how this solution really degenerate a priori in relation with the algebraic geometry. So that is like the global perspective. So today the idea is indeed to go through certain aspects of this story, emphasizing a lot the notion of scale. So we can rescale the metric. That is very natural from a differential geometric point of view. This is how analysts would study often, like in geometric analysis, singularity formation is via scalings. But we wanted to relate this with algebraic geometry, and scaling and algebraic geometry are much less understood. And the plan is going through a toy examples where some of this team will touch upon, but the technicality are not very high. And then I move a more general scenario, keeping in mind an important difference from a metric point of view, namely when the metrics actually degenerate, but they don't go to some lower dimensional space, roughly speaking, so the non-collapsing situation, or we can actually go to some lower dimensional space, making a potential link with algebraic geometry in the collapsing situation more subtle because of disappearance of lower dimensional spaces. So let's start with this toy example. So the toy example are flat metrics on the sphere. So you know Gas-Bonnet, so I think that this sounds a bit bizarre, but what I really mean is actually flat metric with cone angle of the sphere. So this is a completely elementary case that can be understood by hand because the metric are completely explicit. So in principle, in the general case, one of the problems is the metric is absolutely not explicit. It's a solution of a PDE, and you don't really have a control. In this situation, luckily enough, we have that the metric can be written down, so you can explore certain things in relation with algebraic geometry by just computing and play around with the already given solution explicit to the equation. So this is a flat metric on the sphere. You have an example to take a surface of a convex polyhedron, like a tetrahedron or something like that. The vertices are the cone point. The edges are not real singularity. You can isometrically unfold. The edges are not really there. So the only singularity are the vertices. And from more, if you want, a differential geometric point of view, if you want to understand this metric, you want to understand, for instance, the moduli space of these things. So we think now that the points are fixed, and we fix the parameter. We can choose different parameters that are the cone angles, but are fixed now. And up to scaling and holomorphic isometry, actually I normalized volume 1, so scaling should go away. They form some modular space. It has a complete dimension k minus 3. And one can see what happens when the metric degenerate. For generic values of beta, what happens is that this shape don't really collapse to something lower dimensional. The only things that can happen geometrically is that the points collide, similar to Patricio talk yesterday. But now it's really like in the metric picture, we have a metric where these points really get close together and then collide. And one can actually reinterpret this collide of the point to construct a kind of a partial compactification. For generic beta will be a full compactification of this metric. That turns out to, a priori, this you can think that is a rather transcendental object, but it turns out to be algebra-geometrically computable quite nicely, because it turns out to be certain JT quotient, like the most natural you can consider. So you have this marked point, and the cone angle is actually specifying natural linearity we take to do this JT quotient. And then the JT stable point that presides this straight, like the boundary straight when the point collides, is matched perfectly the behavior of this flat metric.
So the beta I, what do they mean? What are
yeah, so here are the cone angle, but here you have, if you suppose that they are rational, then you can take a rational line bundle, like some O to the power probably 1 minus beta or something like that, as a rational for each of them. And this gives a different stability notion. So the cone angle is actually reflecting in the linearization of the J. So this is somehow give a kind of a global picture of this fixed volume scale, but it's not the end. And this indeed is one of the example of this, what we heard, like a K-modular space in this Calabi-Yau situation, in this non-collapsing situation. But one can ask what happens when singularity forks. So differential geometry, as I said, one can do rescale. So you take a sequence of metrics and sequence of points, and you want to rescale the metric when these points collide. And so when you rescale this metric, there is nothing. It's quite easy here to see what happens. You get either some flat cone, but I mean really a real two-dimensional flat cone, or you get a family of metric on C with residual cone point that are still exactly conical at infinity. This is the two things that you have. We call this metric on C with some residual cone point and core at infinity, asymptotically conical bubbles. And you can actually collect all this rescaling by forming what is called the metric bubble tree. We fix a singularity point, a point of collision, and then you look at the set made of all possible rescaling that are pointed at Gromov-Hausdorff limit as the point approach to this clustering point, and they form a tree made of these asymptotically conical bubbles and cone. And the question is, can we compute it algebraically? Here is a picture of what is going on. So we have this polygon, we have this point that comes together. So we have a tangent cone, and the situation is just isometric to the actual, locally isometric to the singular things here, nothing particularly fancy. And then you start along this dynamic process, you start rescaling. So you are trying to not get all the points together, and you will actually get what is called the minimal bubble. This is going to be an asymptotically conical metric that has the cognate infinity equal to the cognate singularity, but still has some residual point. So this means that we have not made all points to really separate. So in a certain sense, there are high order points that are still clustered in this situation. And you can go inductively until you reach what are called the deepest bubble. In the deepest bubble, somehow you have managed to get like all points not coming together. And this is a finite process. And so the question is, okay, this is metric, but can we compute it algebraically, this bubble tree? And essentially the answer in this toy model is a yes, and it's kind of very simple. But the point is not really that, yes, we can, the point of this theorem is that indeed something that about the metric at the end is fully determined by the underneath, if you want, algebraic geometry of complex structure. That in this situation we see by hand, because the metric is explicit. But if you go, as we will see in higher dimension, this is absolutely not obvious that this is the solution of the PDE may still get this property of understanding the rescaling that is indeed purely induced by the degeneration of the complex structure. So I really wanted to focus that much on the content is more like you can compute algebraically. At the end, it's just looking at the different order of clustering of the polynomial. And it doesn't really matter what is the beta, but it's just in this situation, the order of clustering of the polynomial. And so that's good. So it seems that it may be possible to do that. But one can also try to, so here we have a focus about the family that is degenerating. Another thing that one can do is focus on the modular space itself, like yesterday, the space of labels, as we were saying. So the space of label itself has a canonical metric that is called the White-Peterson metric. This is some complex hyperbolic metric. That was the reason why Delin and Mosto were interested in this example for this sort of metric. And it's actually known that if you take this White-Peterson metric and you look what is the completion of that metric, this actually agrees with the GAT stable point. There are some points at infinity, but these are precisely the polystable points. But still, for completion doesn't matter. So the completion is actually identified with this JT stable, as this was shown by Thurston. But one can also analyze what happens about like the infinitesimal structure of the moduli at the boundary in relation with this degeneration of metric. And so one has this complex hyperbolic metric that is a singular actually at the boundary we attach in this compactification. But one can understand some aspect of this metric by computing what is the metric tangent cone of this White-Peterson metric at the boundary. So you start rescaling the metric and see actually a higher dimensional cone that turns out to be some flat cone, but it has a singularity along several divisors emanating. And actually this can be described as some cone over a certain space of hyperplane arrangement, braid hyperplane arrangement in the projective space. So somehow the infinitesimal geometry at infinity has this space of hyperplane arrangement as complex link of this. And the link, and actually there is a link between this bubbling and this cone, because one can interpret this space of hyperplane arrangement as the modular space of the minimal bubble. So remember that there is, when we rescale, a first rescaling that gives some bubble that has a tangent cone of infinity, the tangent cone of a singularity, that are called minimal bubble. And they form a modular space that can be identified with the complex link of the tangent cone of the White-Peterson metric at the boundary. And one can also go further and not just stop at the minimal bubble and continues at a higher scale. And in this situation, one can see that the Delin for compactification, that usually is described in terms of hyperbolic metric with a Caspian singularity at the K point, can also have a different differential geometric meaning in terms of this bubbling of flat metric. So this is somehow the picture. So this now is our flat metric, now it's becoming one-dimensional, that point collides together. This is the limit at the fixed volume scale where point collapse, but you can force points to not collide, and this would create several components like that. These are the components in the dilemma for compactification. But instead of thinking that here we have hyperbolic metric, and these are cusp, what happens is that here we think that we have a flat metric. At this point, we have a cone angle. Now, this is actually the minimal bubble. This is going to have here a cone at infinity equal to the tangent cone in this direction. And at this other point, will still have a residual cone singularity. Then we go deeper, we have this other component that is again some C with some other point. Again, this we have another component. Here we have, in this direction at infinity, the same cone that we have here at the singularity. And so we get this sort of new interpretation, if you want, of the dilemma for compactification that provide actually a log resolution of this JT stable model space. And one would like to refer this as some sort of a multi-scale model space that explore this cluster of points. So this is for the non-collapsing situation, but actually for non-generic values of beta, we can also have collapsing. This corresponds precisely going to the case when we have a JT polystable point, when we approach a JT polystable, strictly polystable point in the JT quotient. And now the metric, they behave differently according to how you look them from fixing the relevant scale. So if you normalize the metric such that they fix the diameter, what is happening is this picture here. Is the metric, they basically converge to an interval. So you see at first the phenomenon, this limited diameter scale, we go to an interval that is clearly not an algebraic variety, so we are outside the algebraic domain.
And you're even outside of the complex domain.
You're
even outside of the complex domain, right?
The complex.
I mean, it's no longer.
Yeah, it's not. Yeah. To say this is something clearly not an algebraic variety. It's even like it's a real manifold with boundary in that situation, but that's okay. Then if we take it to volume scale, actually this space becomes like a line. As we will say before, we should think a little bit more like a point times a line, but we'll comment that this more where the point is the holomorphic aspect that survive, but still you get to something like that. And you can also rescale even further depending on the region, and you get something similar as before. You get the minimal non-collapsing scale. You get now some cylindrical metric instead of conical metric with a residual point. Yes, Patricia?
So you're talking about the object that you will see, right?
Yeah, this is the metric. So we take a point that goes to the polystable point, suppose a point that goes to the JT polystable, and then you plug in this flat metric, and you see what happens to the flat metric as you approach at that point.
So somehow your space, like the monic space, are kind of the same, either JT or the remote, so but the interpretation, the object that you see and the way that you get it is different.
Yes, so actually, before I was in the actually strictly stable locus. For generic beta, there are none polystable points, but if there are, then they are at infinity. Yes, but it is true. Like if you think about the JT, this is just some point coming together. Here I'm just describing what happens to the metric over it. So it will be the same space, but over the point I will give something of different in a different category, like this category of metric spaces. But we have this sort of picture, and one can also ask about the Peterson metric also in this situation. The Peterson metric here is actually it's complex hyperbolic and is actually match a very standard description, a Calabi-Ansatz, as it's called, description of an hyperbolic cusp, and can also build up from some other compact complex manifold. In this situation are flat hyperplane arrangement instead of the positively curved hyperplane arrangement, and you can write down not just the asymptotic cone. This is actually locally isometric, how the metrics look like near this cusp. And you see that if you don't scale, you have kind of a multi-scale degeneration. So if you just don't scale, all these exponentials disappear, and you just go back to a real line. So like if you go to the interactive isometric near this cusp, the actual limit is just a one-dimensional line in this point. While if you rescale, you can see the still collapse, but you can make it emerge the flat hyperplane arrangement that build up this metric. And also this can be identified with the modular space of the minimal non-collapsing cylinders in that situation. So another thing that one can do is vary beta. That is something that I have not really discussed so far. One can also vary betas in this picture to get a family of modular space. And when we vary beta, we can vary beta remaining in the flat regime, but we can also vary beta by changing the value of the Einstein constant to positive and negative.
But it's not a family of modular space.
It depends what you mean. Like it's not. It's the aberrational related.
Locally constant. Locally constant family.
Yeah, they will be locally constant. It will directionally change according to certain rules. I guess. Okay. So we have this family of a modular space, and somehow it's kind of intriguing that it's kind of understood what happens near this flat regime passing from the true limits. In one situation, we have this rugby ball that at a fixed volume would becomes like a real line. But if you come from the hyperbolic side, you would see actually that like most of the geometry is actually localizing volume-wise near the hyperbolic cusp, while the hyperbolic components sort of disappear in the limit process, and they create at this volume scale a kind of a natural continuity in a certain sense through that point. And so these things could be useful for several things. One can try to, we have developed isometric, one can relate, try to compute volumes, passing to the limits, maybe in the Calabi-Yau situation. And there is also some more differential geometric perspective, where you construct some differential geometric moduli space, where you plug in together, really the beta is an extra parameter, and you can create a global moduli where all these things fits together. This is what's the approach of Mazzeo and Chu. So that's the example. So like the main takeaway is that with this idea of looking at a different scale, etc., we get a full description of this Einstein modular space of a flat metric. And we have global and algebraic geometry helps to get global algebraic description, but also encodes aspect of rescaling and give some sort of, if you want, unification principle. But now the question is what in higher dimensions? If we go above, where things get much more difficult because we don't have explicit solution to the Einstein equation. So let's start first with the non-collapsing case. So for the non-collapsing case, what is this setup? So we will consider like a family of Kähler-Einstein metric that are polarized. This fix the values of the cosmological constant, and we fix the volume. Like it's polarized, so it's natural to fix the volume. And we consider what is differential geometry, the non-collapsing the assumption. This is the volume non-collapsing assumption. So volume of you can imagine like a ball of ball, small ball, is actually controlled from below by the standard Euclidean volume of the ball of radius r. So imagine like if we are in two dimension, we don't want like something collapses to a lower dimension. So if it collapses to a lower dimension, like a two dimension should look like a cylinder. So a ball of radius r, the volume will be approximately r in reality, in the limit, and not r squared. So you won't be able to find an epsilon when you pass it to the limit. This is roughly volume-wise saying that we don't collapse, even locally. And this condition is actually automatic if we assume that the values of the Einstein constants come up, cosmological constant is positive by standard Riemann geometry. But otherwise, if we are in a situation like gamma is zero negative, is a condition to impose. Namely, given a family is not automatically true, this condition. You will need to ask this condition to hold. And but anyhow, we are under this non-collapsing assumption, and we can actually take limit. So by Gromov precompactness theorem, we know that if we take a subsequence, they converge to some compact metric space. This is a very weak notion of limit. We end up in the metric category. So a priori, we start with something that was even algebraic. We end up with something that is a metric space right now. But at least it's a very weak limit. We can take it very easily. Now the question is how much traction passes through this limit, how much we can recover on this limit. And so the first step is actually coming from a more analysis, that is the so-called Chiller-Holding theory, that is basically saying that this space is not completely wild. It's actually generically a manifold in codimension 4, and the singularity can also be described in terms of what this rescaling that I called metric tangent cones. But this is a purely differential geometric type of result that applies for general Einstein spaces. But in our situation, we have also the complex structure, that we are taking this parallel complex structure that's come with us, that is even algebraic before getting the limit. So the question is, can we pass it to the limit of the complex structure, the algebraic complex structure as well? And the answer is yes. And this is the Donaldson's theory that says under this polarized non-collapsing assumption, the limit turns out to be a singular algebraic variety of the same type of the one that we start with. So if we start with some Fano, it's going to be Fano, a Calabi-Yau is going to be some Calabi-Yau, etc. And furthermore, the singularity of the complex manifold match the singularity of the actual metric, and you can describe via tangent cones that turns out to be unique. Tangent cones a priori are not unique in this level of generality. And this is a generalization of well-known result in the late 80s by Anderson, Bando, Kazuo, and Nakashima in terms of orbifold compactness result. But now we can do, we want to do this.
Can you go back for a second?
Yes.
So in the second theory,
yeah,
there's no way to make the singularities of codimension larger than 1.
No, you can.
Huh?
Like codimension larger than 1. I mean,
yeah.
they want to be on, like, codimension means if you are in the absolute case, not the visor, they want to be along the visor, a complex codimension true singularities.
No. Okay, you were doing curves, so I can use that example with you. You were doing surfaces.
Yes, sir.
The analog,
Yeah.
even with the equation you plugged earlier,
Yeah.
would be to have for dimension 1 a curve for the singularities of the metric.
But this cannot happen. It's codimension 4.
No, that's the first theory. I say on the second theory,
Mhm.
you cannot have any the metric, the singularities of dimension 2, 3.
No, they would match, so they would be just singular along a point. So in this situation, the only things that you have is isolated orbifold singularity in dimension 4. In general, it's the LT singularity, but it's not a divisor, a singularity along the divisor cannot appear. It's always in codimension, it's in complex dimension 2. So you have an honest KLT singularity.
No, I mean the places where the metric is singular.
Yeah.
Can they be of higher dimension than 1? Or the Kähler-Einstein metric is.
You should imagine that the locus of singularity match. The singularity of the metric is precisely the singularity of the complex manifold. With the tangent cone, we should be a bit careful, but it's not that the tangent cone is what you can expect the naive algebraic tangent cone, but we'll come back to that.
So can this picture be fit into like a family like of varieties? Like, I mean, it's
good point. Yes, no, in the sense this is a pointwise statement. One needs to prove something. If one to show that like there is a compatibility between the degeneration of the complex structure and the metric limit. It's not automatic, and I will come back to this in a moment. Anyhow, like from a metric point of view, very transcendental. One thing that you can do is let's add this limit and construct some in general partial compactification where boundary point at this metric space and now have some additional structure. So this is actually a transcendental model space. You just add them. A priori, this you don't have any. We haven't studied the relation with the variation of the complex structure, so you don't know anything about this. It's just a set, and you equip it with the Gromov-Hausdorff topology. But pointwise is nice. So the natural question, does it become algebraic in a certain sense? So if one takes this degeneration metric point of view, the answer is essentially yes. At least point-wise, I won't really dig too much in this situation when gamma is no positive. When gamma is positive, we are in the scenario where K-stability becomes more important. As you know, in a certain sense, one already knows that the KLT singularity is K-stable. So, but still doesn't say something about the degeneration though. But at least point-wise, it's fine. But in the final situation, yes, one can get that the YTD type conjecture extend to the singular world in the smoother situation. And these actually are Einstein limit space. So in particular, metric space, you can talk about tangent cones because all this result of the previous two theories pass to the level. And in particular, for instance, they have reductive automorphism group because they have Kähler-Einstein metric. And you can use this to slicing and construct actually, as it was done by Limon Shu independently by Odaka, to construct some analytic charts first on this Gromov-Hausdorff compactification, and then you descend some line bundle over it. The CM line bundle turns out to be positive, and you get projectivity. So from this very abstract space, very transcendental, you get something algebraic. So that is basically what is saying, but it's very abstract. And before continuing, a couple of remarks, as we also heard yesterday, there have been important advances in the last 10 years. For instance, now this construction of this modular space, where you focus only on the algebraic side, can be done purely algebraically. So you can, in particular, remove smoothability in this approach, and the construction can be done algebraic, as Jiang Shu and collaborator have done. And there is some replacement, like this Donald Sum theory is a boundless result for Kähler-Einstein metric that is replaced by Virchow's DAB type boundless to the modular space. But in the transcendental, you can relay instead on the Gromov-Hausdorff boundless per compactness, and then the embedding in PN, graphics in PN. And furthermore, more recently, there is a variational approach to solving the conjecture, and Berman-Booksom-Johnson shows that K-stability, even in the smooth case, is fine to get a weak Kähler-Einstein metric. But the weak Kähler-Einstein metric technically is not really a metric. For instance, it's not even known if the metric completion of the smooth locus is isomorphic to original variety. So many things that one can get, for instance, you want to talk about the tangent cone, etc., are not yet available in this scenario. And furthermore, the relation between the topology varying the complex structure and the actual metric is not really available. There is some result of Trusiani, for instance, that in the case of no automorphism, in study what happens to the Kähler potential, that is more within this setting. But the Gromov-Hausdorff would require high regularity to talk about this. And this a possibility that has been explored in the recent years is passing through this notion of a synthetic Ricci curvature that these spaces should satisfy. The moment they get RCD, one is back to the previous machinery immediately. But what if one wanted to do some examples? So this is purely abstract, but what if you want to do some example? So one strategy that one becomes computable, that one can run is this modular continuity methods, as several of you are very familiar with. And the idea is that here you plug in your abstract space. It could be like the Gromov-Hausdorff compactification, could be the abstract K-moduli that we know that are the same. But this is very hard to compute. You want something that is computable, like down to earth. You can actually compute things. And this could be actually, for instance, a specific JP quotient, as we see in the previous example of point come together. So there is the abstract existence of the modular space and the concrete, where you actually say, I know how point collides and things like that. And indeed, this can be done in lower dimension. For instance, a very clear picture would say this is the case of cubic surfaces. It turns out that these abstract K-moduli that tell us about the degeneration actually of a connected component of the Einstein moduli by a result of Lebrun, that a priori analytically is a very kind of mysterious set, can actually identify with the Kähler-Einstein, hence one can use K-stability, but it turns out that match with the classical JT of cubic. And this is super concrete. So you know what are stable, polystable points, very classical. And this actually will give a completely computation of which kind of the pets of degree 3 here are Kähler-Einstein. smooth and one singularity or this toric one. So from abstract, you go to something extremely computable. And okay, there are been generalization of this idea. But what is essential in this idea to get more explicit example of a modular space is to general existential bounds like Birk Airbnb or Donaldson Soon to something that is more effective. So we need to take it down the dimension of the Pn or the family where we find our space. And the most obvious way, I think differential geometric is the one that pops out, is to try to introduce some final control of the singularity and saying that if the singularity are not too bad, then we can still embed some Fano in some maybe smaller projective space or something like that, and then study more concretely. So from a metric point of view, that is very classical. It's like the theory of density. We have Bishop-Gromov with a monotonicity of the volume of the ball. So we have one can define a metric density that is a sort of generalization of the notion of an angle at a singularity. And so it's like the volume of the ball divided like Euclidean. So it's a sort of higher dimensional generalization of angle, if you wish, in this situation. But remarkably, this has a purely algebra geometric incarnation. It is actually a bit better. This constant is better than the differential geometric constants. So the volume is just the degree, the anti-canonical degree in the final case. And this density is what is called the normalized volume of a singularity. So this has origin in the work of Martelli-Sparziau in volume minimization in ADS CFT, but it actually, by Chile notices a generalization outside the toric world and so forth, introducing this new invariant of a KLT singularity, that indeed up to some normalization is the metric density of an eventual Calabi-Yau cone, tangent cone at this point. And so somehow then you want to use this invariant to stratify like the singularity. The one that have this invariant, the density close to one, as one is a smooth space, and if it's sort of a bit smaller than one, it should be a bit singular, but not too much. And indeed, there is some sort of stratification. For instance, there is a first gap one can imagine, like the simplest possible singularity you can imagine is an ordinary point, and indeed is gapping, at least conjecturally, is gapping dimension 2, and it actually also gapping dimension 3 by some result by Liu and Xu. In general, is this volume hat has no accumulation points beside the origin. So it's actually, you can get some sort of control, stratification control of the singularity type via this normalized volume. And these are important because they actually put constraint on the kind of singularity you can then find, and these can be good to find if you want new classification of mildly singular Fano with volume controlled, and then you can get effective bounds out of that. But this normalized volume is not just important for this, it's actually important even for computing the metric tangent cone. So it turns out that this normalized volume come up with, there is actually a function I want really to define that is defined on this, what is called the non-Archimedean link of the singularity, and that is basically the space of valuation center at this singular point. And there is a function, and this function actually has a minimum. So there is a specific kind of canonical valuation above this point. And this valuation can be used to compute what is the metric tangent cone by taking the associated graded, and then in general, there is a further test configuration to the Calabi-Yau cone. So this is called the two-step degeneration. So, and to remark the relation with the singularity of the underneath manifold, you see that if you find a K singularity like in dimension 3, so this is an isolated singularity, but the metric tangent cone is no longer isolated. So this the minimizing valuation has these weights, and indeed the metric tangent cone is this non-isolated singularity C2 C2 times C. So the moment that you see in nature a lot of Kähler-Einstein with this isolated K singularity for K equal greater than 4, the actual even is an isolated singularity, the metric tangent cone is not an isolated singularity, it's a C times C2 mod C2 cone. So this phenomenon happens. So compute a tangent cone is actually going back to what we have done before. After a tangent cone, we want to compute these bubble trees that also can be defined in this situation. So you can rescale the metric, you get not just the cone, the Calabi-Yau cone, as we described so far, but also this asymptotically conical Calabi-Yau. And one can plug in all together in a tree, as we did before, and one can ask the similar question, can one compute it algebraically? So part of this theory, like the dimension equal to 2, at least for the general existence of what are the bubble trees, very classical again, the same people as before. So these non-collapsing bubbling are parameters A spaces and or quotient of it, and it could be still an orbifold version of it, because if we linear scale, if it's a minimal bubble, can be still singular. That don't need to be smooth. But there is also the more abstract, higher dimension. So these are classified, it's super clear. There is also a higher dimensional version of it, where they also exist. These are going to be a fine Calabi-Yau, and there is also some sort of finiteness of this bubbling related to that. Like given a singularity, you cannot, and a sequence of points, you cannot get many different up to scaling bubbles in this situation. So there is some hope that you can indeed do algebraically. It's not completely disconnected. So that's the question. So given a polarized family, we pick a point, can we compute algebraically these bubble trees?
But, in the one-dimensional case, you actually have like quadratic loop along three,
Yes,
right?
exactly, yes.
Graph.
Yeah.
But here is
That's the conjectural pictures. There are certain examples that suggest this, we say the moment, but like the general answer is not available yet. And especially this jumping create a lot of difficulties. The fact that the tangent cone is not locally binomorphic to the original one means that even in the deformation theory of the original guy, you don't really see the actual bubble. It's not like in the Granici space of the deformation of the singular guy, but it's jumping, and this creates a lot of difficulties. If one wants to relate to algebraic geometry, one can start to experiment a bit. And for instance, in dimension 2, if everything is known in terms of the differential geometry, we have this equilibrium bubble, but how we can go in terms of relation with algebraic geometry. So for instance, if you take a case singularity and you smooth it out, here you can do some, again, toy computation, where on this partial smoothing or or whatever, like this, you plug in not so this is not a situation in the sense that they will plug in as a metric actually one of these gravitational instantons, and we take one a particular one, an affine gravitational instanton on the smoothing of the case singularity. Themselves bubble off. You can take a family of them, and they can itself bubble off. And one can ask, okay, for this family of a standard gravitational instanton on the smoothing of a case singularity parameter type, and we understand the bubble tree out of the equation of the smoothing of the variety, and the answer is again yes. You can actually see that you can get it for certain rescaling, weighted rescaling, but this weight, the important thing is precisely the weight given by the normalized volume before. So somehow the actual scale has to be done in the direction of the cone computed with this normalized volume.
So the scaling is not arbitrary, it's actually very
yes,
precise.
there is a precise value when it jumps. You get a first interesting jump at the next scale. And so this is purely local, but a joint PhD student with Odaka have shown that this local picture actually is also global for K3. There you can use period computation to see that this picture here is actually really occurring for bubbling of K3. Thanks to Rayleigh type theory for gravitational instantons in that situation. And furthermore, one can blow up in the modular space of K3 and the non-collapsing, so-called Henger divisors, where when there are these AD singularity forms. And by doing certain iterations, blow up, you can actually construct some sort of multi-scale K moduli analogous to this Deligne compactification in the original case, also for this case situation. So this leads to a general conjecture, probably a bit too technical, but let's say just in word. Now, so there is some evidence, as we are saying, but it's conjectural. The idea is that given a family, you should be able to algebraically compute what are the tangent cone, but unfortunately, the tangent cones would live on a deformation, and the bubble would live on a deformation of the tangent cone. The tangent cone arrives via two-step degenerations, and so also the bubble is a bit tricky because it's also related to these two-step degenerations.
When you write AG computable, what does that mean exactly?
Computable means that you don't use differential geometry, but you can use some algebraic geometry with some valuation, some variational geometry. The idea would be
that explains AG, but computable. How is that?
yes, okay, that's probably different. It's a big word. Like there are different levels. There is a conceptual word that you just need algebra geometric tools to compute it.
Yeah.
Then there is, can you actually compute them? That is a more effective. I'm computing what is the affine Calabi-Howe that support a metric.
The actual equation.
Yeah, the actual equation, the actual affine space that support an asymptotically conical Calabi-Howe. That is the first rescaling of this family of Kähler-Einstein metric. And the idea is roughly that you should first compute the evaluation and apply some variational geometry to do that somehow. I think that's a bit.
It's very vague.
Yeah, it is vague. It's more like it's not a precise conjecture. It's a kind of motivational conjecture.
Fair.
Yes, but yeah. So it's in a certain sense, that in Word you should really think that with some algebraic technique using computing the evaluation and do some variational geometry, you can actually figure it out what should be this bubble.
So even if you don't have equation, but you have, I don't know, like some cohomology, some degree, that already would be helpful.
Yeah, at the end, we want to understand what is the actual space behind it.
Right.
So, yeah. So in a certain sense, you wanted to make it precisely heuristic, as I kind of say, like we have a family, we take a section, a point, and we wanted to kind of describe the structure of this space, is sort of getting an expansion of this space, where we get the first is the stable limit, but then we have all these other spaces that, as Patricia was referring to, probably are glued together in a certain sense, the three. And they would correspond to like looking at a different scale at the moment that we approach the singularity. And in principle, one can get these kind of things. An analyst would say, let's do a gluing, but gluing is a bit limited. You would need to already know that the space have a Kähler-Einstein metric, and then you try to glue back. In a certain sense, we can approach it in a more a priori way. If one can prove the conjecture as before, you just say, okay, I take this degeneration, then I know that there should exist some Calabi-Yau metric on that affine space because they appear as a rescaling of the compact one, not because I already know that exists because they know. And indeed, this is not completely out of the. There is some ground on that. For instance, if you just form ordinary double point, the result of Song-Soon already says that the stencil metric has to bubble up. You don't need the glue. You just need the strong result of uniqueness that are available in the situation. Like ordinary double point has a trivial deformation space, one-dimensional, and in that situation there is a unique asymptotically conical Calabi-Yau that is stencil, but Song-Soon has proved that there must always be an asymptotically conical Calabi-Yau with that tangent cone. We can compute the tangent cone, we know that it's stencil, so there is the stencil cone, so there should be the stencil bubble as well.
Sorry, the original part, this loss of B, are they the same dimension as the zero? They are smaller dimension?
No, these are same dimension. These are really components. They should be really reducible components. The lower dimension would come up in the next few slides, sort of 10 minutes. Before moving to the collapsing a bit, let's say that we start at the beginning with pairs, meaning metric with conangle. These things actually can generalize also in this situation where we can consider pairs. But keep in mind again that we are talking about these bubble trees and things like that. And we face this issue that I said that if we take like the variational solution of the Kähler-Einstein problem, we cannot talk about bubble tree because we need more regularity of the actual metric structure to talk about bubbling and better bubble tree. However, this is doable if one can get in this RCB category. And one can actually show that if you take some generic device, like simple normal crossing device, Kähler-Einstein metric, that is with Kähler-Einstein metric, turns out to be actually giving rise to RCD spaces. And being RCD spaces means that we can take the Gromov-Hausdorff limit, and the Gromov-Hausdorff limit with a metric tangent cone and so forth. So if one wants some higher dimensional version of the original picture, the obvious one would be modular space of hyperplane arrangement in PN. Generically, appropriate arrangement would be simple in some simple normal crossing conditions. So we know that the actual weak solution is actually an RCT space, and so we can actually take limit and basically do, even in this sort of non-smoothable pair version, what is done transcendental. And but I wanted to, in the last sort of 10 minutes, move a bit on the collapsing. 5 minutes, yeah. So there are two cases. The one now we divide the case according to the value of the Einstein constant. So when the constant is negative, we are in the negative Kähler-Einstein case. And now at generic at volume scale, the picture is pretty understood by now. And we actually analyzed the linear story. So one knows that a stability is equivalent to some condition of the singularity. In one dimension is the Riemann stable and the nodal singularity, and here is kind of KSPA stable. But it's also known at the generic volumes, at the volume, that the metric actually converge to some metric on the reducible component, metric of finite volume on the reducible component of a K-stable degeneration. This is the result of Yang-Song. There is actually, so here is we are analyzing the generically non-collapsed region, but there could be a region where it collapses. If you take some hyperbolic surface, two-dimensional surface, there is the hyperbolic corner where you actually collapse in that region. So away from that, you don't collapse and you get to this hyperbolic cusp, but there's still the corner region. So this is why I said that there is a local collapsing in this situation. And but here the situation is, one can want to understand what happens. So generic at the volume scale is understood, but what happens near the collar? And this I would say that is not yet completely understood. So especially in relation with algebraic geometry. So we know that we have this, for instance, when we have this local collapsing, we are in presence of strict semi-log canonical singularities, and we want to understand what happens nearby. There are some differential geometric results, but an algebra geometric framework to describe what happens is missing. The only things I wanted to mention is that maybe there is some hint of what is going on if one analyzes a certain example. I had a few years ago a student that analyzing this perspective, the natural metric on the hypermodular cusp. And here the metric actually collapsed down to a cylinder, S1 times R. If you write down coordinate, is obvious. But what is the meaning of this S1 in terms of algebraic geometry? So this actual singularity very classically have a very famous minimal resolution given by a cycle of P1s. And somehow you observe that if you take some natural map, what's called a Thomson-Johnson map, you can identify the circle that appears in the metric degeneration with the dual complex of the minimal resolution. And actually, this is sort of example generalized a bit in higher dimension as well. And so a bit like, again, an heuristic picture, first things that one could imagine is that in general, this dual complex may play a certain role, the dual complex of some minimal DLT model technically, and you needed to restrict yourself on what is the sort of essential skeleton in that situation where the log discrepancy is 0. So it's a bit technical, but anyhow, essentially the idea is that the dual complex of certain resolution of singularity encodes certain information about the behavior of the Kähler-Einstein metric that otherwise remains very mysterious. That's the picture. We have a local canonical singularity, and when you want to go to the cusp, and somehow the geometry at infinity is covered by the dual complex of this minimal DLT model. And but in the last few minutes, I want to say something about the Calabi-Yau case as well, where recent advances make the picture, the conjecture picture a bit more, or at least at a heuristical level, understood, I would say. So now we consider polarized Calabi-Yau, but the problem is that if you want to do modular space, they collapse not just locally near the singularity, like in the curve case, but globally. All the space collapses to some lower dimension. So if we care about the relation with algebraic geometry, we have problems. And but in particular, if you want a kind of a projective algebraic compactification, and one thing one can also consider is the By-Petersson metric. Also here is very explicit in such case, the By-Petersson metric. and one can try to see if there is any relation between the distribution of metric and some sort of projective type compactification in situation. So again, here, the understanding of the different scale becomes crucial. There are like at least 3 levels of scale that, from a metric point of view, have a different meaning. There is like, if you look at the larger scale, that is the diameter scale, this is the one that has been studied a lot. You get the Gromov-Hausdorff precompactness, is the one that has been studied in relation to mirror symmetry and so forth. But you can also rescale furthermore the space. You can get the volume scale, where you fix the volume. This is very natural if you consider polarized Calabi-Yau, for instance. And there are even larger scale, like if you zoom even further. And this is related to Calabi-Yau bubbling, but I won't really wanted to discuss about that today. I wanted to fix about these first 2 interesting scales in the Calabi-Yau situation. So again, example in higher dimension of that on this H scale. Okay, if one goes with abelian varieties, polarized abelian variety, this can be computed by hand again. And the diameter scale compactification actually can be identified with, so the polarized abelian variety are locally symmetric space, and there is a certain compactification of locally symmetric space, the Sataka joint, that is not algebraic, it's a tropical compactification that match the diameter scale. But at the boundary, you plug in real toric, but these are kind of a dual complex of semi-abelian degenerations, not really algebraic variety, but a dual complex of them. If instead you fix at the volume scale, actually it turns out that the compactification can be identified with the Bailey-Borel compactification, and this is projective algebraic. So we are back in a more clear standard algebraic way. And the point at the boundary, even though the Bailey-Borel is defined by a theory of locally symmetric space, it's not obviously have an immediate modular meaning, but it has in terms of parametrizing essentially lower dimensional abelian varieties at the boundary. And this splitting have a postdoc that have verified that is also seen at the level of the asymptotic by Peterson geometry as we described in our example. So there is some holomorphic part and a tropical part appearing generically as we approach it to the infinity. The next case would be to analyze this would be K3 surfaces. So if you do K3 surfaces, you can do this at the diameter scale. So this was the first observed by Odakoshima, and then a bit more general for a certain point, and even in an polarized case by Wang and Tian last year. Yes, sir, just 1 minute SHP I conclude. So at the diameter scale, you get similar the Sataka joint that also lives here. But one can ask what happens at the volume scale. And at the volume scale, what happens in short is, again, the Bailey-Borel appears. So this is some kind of work in progress. We are kind of cleaning up this one part. But again, Bailey-Borel appearing in sort of a generic sense. Like if you take the generic Gromov-Hausdorff limit, they would split a flat elliptic curves times R, but period. So we're identifying this elliptic curve with the boundary of the Bailey-Borel. There is some decoration because the boundary of the Bailey-Borel is a modular curves, so there is some further decoration. But essentially, besides the decoration, you will get this identification. By Peterson metric is similar, and there is some other refinement I want to. So to conclude, let's go to the general conjectural picture. So at the diameter scale, the conjectural picture is sort of understood. It's a sort of a generalization of the Defonsevich-Soyman perspective on the SYZ conjecture. So you would expect generically limits to in the at diameter scale not to be algebraic variety, but a dual complex of certain degenerations. So we go outside the category of algebraic variety, but we go to this more tropical dual complex of varieties. And there is a lot of recent work, for instance, by Yang Li, but other people in the past, Sun Zhang, that have verified this one in special cases. But what happens at the volume scale instead? At the volume scale, now the idea is that generically, you would see at the volume scale the appearance of lower dimensional Calabi-Yau times some RS. RS is actually the tangent cone of the previous scale. So this RS appears as the tangent cone to the generic point in the dual complex. But then something that was disappearing is still emerged, and these are lower dimensional Calabi-Yaus that are realized as Collar sources or local canonical centers of certain stable degeneration. So the geometry localized near this local canonical center. And And in conclusion, this suggests that if you look at the volume scale, that is the one where you look at K-modular space in general, it seems naturally that the natural projective compactification boundaries is some sort of boundary that parameterizes classes of lower dimensional Calabi-Yau, going back to Patricia questions. And this is likely to be projective algebraic, at least because also the bipital matrix C these holomorphic components. And it's very likely that in reality it's deeply connected to this new compactification of Hodge theoretic by Baker, Filipazzi, Maury, and Zimmerman that use Hodge theory to get some compactification. And somehow one can test how much this picture could work, for instance, in looking for modular pairs, because like in this one-dimensional case we observed, somehow this fixing the volume works, this unification, one can wonder how you would do in general. So, yeah.
Very much. You're right. I think we've got time for maybe one quick question.
Yeah, I have a question. At the beginning, you gave an example, I'm not sure if it was a lemma or a theorem, on how to do AK.
Yes, sir.
For CPU, for dimension 2.
Yes.
Well, what about other ADs?
I think that it's like we did the AK because we have the Gibbon-Hawking ansatz in terms of
Okay, actually, you did A2.
the example is a true, but
But you did already
AK.
So could other ADs be done as well?
Not with the same approach, in the sense that we use the Gibbon-Hawking ansatz description, and this is available for a K. But for instance, for K3, you can do periods, and the periods actually works even K3 can form singularities and worse of type D and type E, and there you can still compute the bubbling, but using periods instead of Gibbon-Hawking's and the relativity theorem for gravitational instantons of a band.
Okay.
All right. Thank you very much.